Now we're gonna move to another interesting part is what happened here is not only happen in one dimension, it can be in 3 dimension. However, most of the example, if we're gonna move to the 3 dimension, we're gonna state about 2 dimension first. If you look after the snooker table, if you have the ball from the initial position to hit the rest ball, this is at rest initially. This is the initial velocity of the ball M1. When it hit to this part, this is before collision. And this is at collision. This is after collisions. It still conserve the momentum. So you can use the conservation of linear momentum, sigma p I equal to sigma pf. But be careful, you have to write it in terms of vectors. Think like a vector. So because the direction component can change, you can rearrange the components with the theta here. If you got the theta over here, with the close to theta, you have cos theta components. You have sine theta for away of the theta. If this is a phi angle, you have phi angle over here. With the close one is cos phi and another sine phi. If you sum up this term, you can see this is the first event. I would like to emphasize the key again about the conservative or the conservation of momentums. If this initial momentum, you have the orange arrow to represent the P initially as a vector. When it do a collide, the total momentums or net initial momentums should be equal to the initial momentums. Even finally, after a collision, you have seen this ball moving another way and this one another way. But when you sum up all the momentums, the net momentum should equal to the same of the initial momentums. This is how we call the conservation of linear momentums. And all these components, as I said, you can use the vector or the component breakdown or combination to get whether it's sigma p along x-axis or sigma p along y-axis. You can break a component if you want, or you can make it together by add the ijk sign to indicate about the vector directions. Let's look after this example. This is happen when a car that moving from 2 different positions in 2 dimension and crashed. And finally, they move together as well. This is still another kind of inelastic collisions. What we would like to determine, the direction and magnitude of the velocities. So we would like to determine vectors of the velocities after the collisions. Since you look after here, this is maybe I claim it as a mass 1. This is mass 2 with the blue car. You have the mass 1 has the initial velocity as u1, and for the blue car as u2 as the initial velocity. After it clash, m1 and m2, they stick together. It's like wreckage. Others assume vehicle stick together. So m1 and m2 have the same terminal velocity, which is v. So now if you consider about the conservation of momentum, you can use sigma p from the initial state equal to sigma p from the final terminal state. If I like this is at the state 1 or state 2. Or if you don't like to have the same 1, 2 things, you can write as initial and final. Or write it as the initial and final. So as a vector, so you can sum up all the initial vectors. So it's m1u1 plus m2u2. It's gonna be equal to the a final event of the net momentums, which is m1 plus m2v. We would like to determine the direction and magnitude of the velocity, the wreckage after the collision. So that this is what we would like to determine. So that we can rearrange the term. We would like to determine v, which is equal to 1 over m1 plus m2 multiplied with m1u1 plus m2u2, like this. And you can see u1 is equal to 25i direction, u2 20j direction. So by this you can sub all the information in. So 1 over m1 plus m2, m1 is 1500 plus 2500, finally you got 4000 for m1 plus m2. And m1 we write below for the better writings. 1 over 4000, and m1 is a car traveling east, so this is m1 1500, and the north traveling is 2500. So you have 1500 with the direction eastward side, and velocities is 25i. I will write with this one so that you can see it's as a vector, and plus with 2500 with velocities of 20j. I'll be moving upward, northward. This, so you can do a multiplication on it if you would like to determine about the velocity. So when you sum all the value in, finally you're gonna get the 4000 for get rid of this part. So this is supposed to be 125 over 8i, and then plus 100, right, over 8j in meter per second. This is your v. If you would like to determine the magnitude of it, you know how to find the magnitude, right? The magnitude is the components, and you squared it up. So you square it up and plus. So finally, you get magnitude of the velocity equal to meter per second. If you would like to determine the angle or this theta, what you have seen, this is the components of v along x direction. This is the components of v along y direction. So by this case, you can see vy over vx. This is your vx. This is your vy. It's the tan theta. So that if you would like to determine theta, just find arctan of vy over vx, which is 100 over 125. Finally, you get angle around 35.1 degrees. Right. These are answers that you can use the knowledge of the momentums, the net momentums derived as a vector, and using the conservation of momentums to find out the terminal velocity after these collide together, and know the direction that it's moving forward after the collision. This is another example of how you use the knowledge of the conservative of momentums in a snooker game or like a pool game. or we can call it like billiard, for example. So in this case, a player wishes to sink a target ball in a corner pocket. So which is the initial event is you have the cue ball or the white ball this with the initial velocities, and this purple ball or black ball is with the zero initial velocity. After you hit this ball onto the black one, it have the terminal velocities v2. If I state this is as mass m2, this is mass m1, this is mass m1, this is mass m2. You see this angle. If you would like to determine the angle after the collision, so you like to determine the angle of the white ball after it's collide, so you should guess this one not going to another hole, right? Because if you get the ball, the black ball get into the hole, and this one get to another hole, the game not gonna end. So you're gonna get some how to say the deficit point from this play. That is how you like break rules of the billiard. So you make all the color into the hole except the cue ball or the white color. And these things is we assume in the case that there's no friction and there's no rotation yet. We will learn about some angular momentum, some rotation later. But in this case, we not state that our billiard ball or snooker ball rolling or with some friction. So we not claim at this state. We said it's still moving freely or sliding with the velocities. These are the claim. How you can derive this? In general, this is looked as elastic collision, right? If you see the system of these two balls as elastic collision, you can say that you can apply with the conservation of the momentums, and you can use the conservation of energy, or you can say that energy that happen only the kinetics energy, just the conservative or kinetics energy. With these two relation, the first one and the second one, you can use to determine the angle. If you look after the components that you have here, I will break down all the components here, and later I will show the step by step of the calculation. If you break down the components, you will see your V2, V1 first. Your V1 is in I direction. So if right vector, V1 in I direction. This is your U1, sorry. What happened before a collision? But after a collision, and U2 is 0. After a collision, I will write as I and F to reduce the confusion. I and F. This is before collision and after collision. So what happened after collision? You see your components of V2, which is from mass 2 here, this is V2, is the component both, you have the magnitude of V2 cos 35 in I direction and also V2 sine 35 in J direction. However, the V1 terminal velocity of this is from mass m1, this is from mass m2, this is from mass m1, this is from mass m2. With this part, you see your V1 is downward, so that you have component of V1 cos theta I, since you would like to determine this theta, and you have minus. This is minus because it's pointing downward. You can state axis as upward as a positive j, and right handward is a positive I, which is plus x and plus y. So this is the reason of the negative sign here. Negative v1 sine theta j. So these are all components of velocity. If you would like to find the momentums, just a mass of individual one multiply with it. You would like to find p1, just mass 1 multiply with v1. If you would like to determine the momentum of mass 2, m2 v2. So now we have all components and ready to do a calculation. So we can start with the conservation of momentums, which is sigma p I equal to sigma pf as a vector. This is the pi and this is pf. If you would like to write it as a vector, you can do it. But if you would like to break a components, I will show you another way to break a component and do a calculation. So think about, if you look after x components only, so this is your sigma px is equal to sigma px, x of initial condition, f of final condition. What happened in initial? Just only moving a right handward from the cue ball. So this is your m1 and with the velocity. In this case, not only you have m1 and m2, both of the ball, all of the ball have the same mass. So that means your m1 equal to m2 and equal to m. That's why rather than write as m1 and m2, you can write m instead. And finally, you see, it can get rid of each other. That what we state from initial already, which is you have this v1i, or I write as u1 here. So another initial and final event, you get this term along x is your v2f cos 35. This is your v2f cos 35, and you will have v1f cos theta. This is v1f cos theta. As I said, you rather write like this, or you can write as u1 equal to, this term is your v1 cos theta and plus your v2 cos 35. This is your first equation. You can write like this because mass is equal. You can get rid of it. How about in y direction? As you can see, initially there is no momentum along y direction, so the net momentum is 0. After a collision, this one, it have x components already, so another y components is v2f sine 35, and below one is v1f sine theta. So this v1f sine theta and v2f sine 35. Again, you can write in terms like this, or my preference is 0 equal to, because I'm gonna get rid of each other. So this is what you get, v1 sine theta plus v2 sine 35. This is your second equation. And the final one, using the conservation of kinetic energy, which is sigma E1 equal to sigma E REI equal to EF, or K that you have left around here. And again, m can get rid of each order. So with this term and 1 over 2 as well, you will have the term of u1 square equal to v1 square plus v2 square. This is your third equation. Since you have these three equations, now you can rearrange the equation 1 and equation 2. If you square it up, this is what I have. I square both of the equation 1 and equation 2. So finally, I get this is as u square 1 equal to v1 square cos square theta plus v2 square cos square 35 and plus 2 this supposed to be v1 v2, this is the wrong one, sorry. v1 v2 cos theta cos 35, right? The square up is like you have a plus b and you square it up, so you got a square plus 2ab plus b square. That is what you do with the first equation. And the second one, you can also do it as well. So you're gonna get 0 square equal to, this term is your v1 square sine square theta plus v2 square sine square 35 and minus with v1 v2 sine theta sine 35. Now, if you have these two equations and you check it each order, like you do sum of each order, so what you're gonna get, you can compare with the fourth one as well, because you have u square equal to v1 square plus v2 square. I will note here, got u1 square equal to v1 square plus v2 square. Somehow, when you sum this term up, you have this term as your u1 square. You have this term is similar to this. This is also u1 square as well. So now you get this term, which is v1, v2, and some cos function inside. All these will get rid of each order, right? You have this term equal to zeros. So that means the significant value is inside to determine the theta. So this is what you got. You got cos A cos B minus sine A sine B. From the trigonometry characteristic, with this we will know is equal to cos A plus B. Right? So what's significant here is here the theta inside. So that means you state that what make cos A plus B equal to zeros? That is cos 90 degrees. And that is how you can use this information to determine the theta, since 90 minus 35 is equal to 55 degrees. So this final angle is 55 degrees.